All right, so no questions. Let's start. So today I'm gonna be continue talking about. I will finish the topic of the previous discussion about logical statements, and then I will turn to uh, practicing more uh, formulations from textual problems. Um, so the one remark that I wanted to explain logical conditions is the following. Imagine a case when you are really struggling with putting down the reformulation of your logical condition to a system of linear inequalities. Let us take a look at the example. For example, I know this one. Let's say that we have this example here, and we would need to construct this inequality here, just as for example. First thing that we do is constructing the table. That is algorithmic steps. We know how to do this, and then the question is how to make the step from a table to the inequality. One picture that can help us in case we are only dealing with 2 or 3 variables would be to is the picture of our sets of our set, or basically we would need to draw a hypercube, a cube or a hypercube with the logical variables. Here is our x1, here's our x2 value, and we would need to denote what exactly are the values that that belong to our set, to the set that we are trying to express, and what are the values that do not belong to the set. For example, in this particular instance, we have that the points 1, 1, 1, 0, 0, 1 belong to the set, and the point 0, 0 does not belong to the set. So let's draw it. If we draw it, we will get that this point, and this point do belong to the set, and this point doesn't. And it is kind of obvious that if you basically make any linear constraint that separates the point that does not belong to the set from the points that do belong to the set, this linear inequality would do the job. So basically, we just need to come up with any linear inequality that separates that allows us to separate the these 3 points into the set that is allowed by the inequality. One of these inequalities is this one. So this is not therefore this is not the only formulation, because any kind of inequality that has a similar property would work for us. In 3 dimensions, I will just draw it without writing down the formulas. Let's say that you have this hypercube of 0, 1 values, and you are let's say that the points that do belong to the set are these ones, this one, potentially this one, and and all of the other points do not belong to the set. In this case, you would potentially need first of all, it would make much more sense to formulate the inverse of this condition, because it is easier to actually express the points that do not belong to the set, just because they are in the same component of like they belong to the same component of connectivity. So what we would need to do is to come up with 2 hyperplanes in the cube. You can just imagine that there is a hyperplane number 1 that goes through these 3 points, and there is also hyperplane number 2, a plane in this case, just a plane number 2 that passes through these 3 points. This one, this one on that edge further down, and this point. And these two planes, if you just select the space between them, the space that they are limiting, they will give you exactly a system of inequalities that would formulate this set of logical conditions. I just need to stop here and see if there are questions, if you would like me to go into more details on this.
Just to be clear, so you're saying for this 3D case, you have like the two points on the end, and then you're basically saying you're cutting like, you have like a cube, and you like kind of like
I'm cutting it twice and selecting the area between the two planes, and they will like this six points here, they will belong to that area, and all of the other points.
Oh, we actually want the circles. There's like the points that are circles.
So you can just imagine that you are expressing the opposite condition. You can just say that the circles are now the cross, so it doesn't matter.
Yeah, that's so in that we're cubing two hyperplanes, and then it's either the area in between or the area outside. And we
exactly,
okay, that makes sense.
That is right. Yeah, that's a good question. Any other clarifying questions here? Okay, so this was an example of how to construct a linear inequality, or a set of linear inequalities. One way to do it. Okay, let us focus on textual problems and formulating them in mathematical terms. This time we're going to be dealing with a problem. Oh, by the way, I did not ask this question that I asked last time. Do you have any preference in which we go over the problems? Because we might not have time to cover all of them. I would like to cover those that are in preference before we switch to everything else. If you don't have any preference, that's cool too. So let's start with this job scheduling. We consider the production of a single product over T periods. We actually have done this this exact problem on the lecture, so we don't need to do this once again. Okay, let me skip through this. But there are, okay, let me remind you real quick. So we consider that the production of a single product over T periods, if we decide to produce at period T, a setup cost CT is incurred. It was FT on the lecture, but now it's CT, doesn't matter. For a finite horizon. Let DT be the demand for the product in period T, and let PT and HT be the unit production and storage cost respectively for period T. So these two are being scaled with the number of product that is being produced or being stored in the period T, and CT is the cost that is incurred no matter how much you produce. Just if you produce, you do suffer the loss. So we did formulate this problem during the lecture. Just as a reminder, if we like our very first formulation was that we had a binary variable that indicated if we produce in period T or not. We had the amount of production, and we had the amount of inventory that is being like brought into the next time period. So the amount of inventory that is being passed from period T to period T +1. Then we are adding more conditions to the problem. So now we're going to be adding more sophistication. Suppose that we allow some demand to be lost in every period except for period capital T. at a cost of BT per unit of amount of demand lost. Show how to modify the model to handle this option. So once again, what is happening if we have a choice not to satisfy a part, some part of the demand, we incur BT for each piece of demand that we did not satisfy. We need to add a new variable in this case. The solution for this is to add a new variable, that is the demand loss in period T. We have to take into account the fact that it may be optional to not satisfy the demand in period T, even if we could, in order to use the saved storage for the next period. So basically, what it's saying is that our equation, our balance equation that we have had before, is now going to be modified in a specific way. So now this is going to be our balance equation. You can see that there is this term being added because we did not satisfy, basically we are subtracting a demand of DT minus LT, because now we are not satisfying a part of the demand, and this is our new demand that we have decided to satisfy. Most of the other basically we modify only the balance equations for the time periods that are not terminal, except for the last time step. And also we are saying that our demand not being satisfied must be less than or equal than the total demand, just because we cannot unsatisfy a negative demand. That's pretty much it. That's what difference it makes to the this addition makes to the constraints. And then we need to remember that we need to add an additional term to the cost, to the total cost, because we incur a loss LT for each, loss BT for each of the LT units of demand that we do not satisfy. Any question here?
Just want to confirm the thought process. When we're adding this L sub T loss, or the loss sort of variable, we could also just opt to not add the variable and just create extra constraints, right? For example, the top, we could have we could not have the L sub T, and then the top equation would be an inequality. And then we just modify, it would look a lot uglier, and we'd have a lot more things, but we could theoretically do without the L sub T, right?
It could be that you're right. I just don't see exactly the way that you're proposing to make it. Can you formalize it somehow?
I guess L sub T would just be the difference between the capital IT. It's definitely a lot more confusing. I'm just trying to confirm theoretically we could probably
there are multiple formulations for this problem, that's for sure. And we did see we did see a different formulation than this one during the lecture. So if you were to come from a different that different formulation, that extended formulation that we have had on the lecture, then you would definitely arrive to a different formulation here. So there's definitely multiple formulations for this. I'm not sure you can completely get rid of just completely get rid of introducing new variables. I'm not sure it's possible here, but it could be. I would need to think about it. That's a good remark.
Okay, I was just wondering because, but obviously it's a lot worse, or it would be a bigger headache to figure out whether or not you can. So that makes sense.
Yeah, there might be some benefit behind formulating in the less number of variables, in a smaller formulating a problem in a smaller number of variables. But normally people tend to do the opposite. They add variables so that the formulation is more tight. So it actually normally people are not thinking about how to get rid of variables, but how to add more of them. Okay, so let's add another sophistication here. Suppose that production capacity can occur in at most 5 periods, but now 2 such periods can be consecutive. show how to modify the model to handle this option. Basically, what they are saying is that we can, first of all, we cannot produce two periods in like two consecutive periods of time. Let's say our machine needs to take rest or something like this, and the total number of periods that we can produce in is 5. Let's say that we have like days of the week, and we only have 5 days that are available for people to work on. The solution for this new caveat would be to add the following constraint. First of all, the number of, so then just a reminder, ZT was the indicator that we are producing something in period T, and the sum over all of the periods of ZTs must be less than or equal than 5. This will ensure that we do not produce in more than 5 days ever. And then for each J, we just need to ensure that between the time step J and the time step J plus 1, we only produce anything in only one of them. So basically, we are saying that ZJ plus 1 must be less than or equal than 1. Then, like it would be equal to 2 if we did produce something in both days. But we enforce that it's not equal to 2, and can only be equal to 1 or less. So this is like I didn't write down the full formulation, but yeah, I assume that you understand that we can just add this to the previous formulation and get the full formulation for our new problem. Cool. Let's switch to the next question. It's the planning for move. Suppose that you are planning to move into a new house. You have n items of size AJ, and you need to realize how to pack those items into boxes. You have rented a truck that is of size Q, and you have bought M boxes. Box I has size BI. We ignore the fact that the items have like different shapes. For us, all of the items are liquids. So as soon as they have a volume or a size of AJ, we can shape them into any form so that they fit into box as soon as there is volume in the box that allows to fit. So right, we cannot carry items without a box because that would be unwise. We only need to pack everything into boxes, all of the boxes into the truck, and then transport the truck to our new location. We need to formulate an integer programming problem, and I would say that I did mention all of the assumptions. Yeah, so let's switch. Let's go right straight to variables. The variable zi for each I, meaning for each box, would be just saying if we are taking a box into a truck or not. So there's an option to, like, even though we have bought the box, we just ignore the fact that we have it and don't put anything in the box and leave it at home. Xij would be a variable that is indicating to us that we have put an item J into a box I. So basically, both of these variables Xij and Zi are binary variables. Therefore, our eventual problem is going to be binary, which is good. The formulation is the following. So we would like to okay. So essentially, this is one of these problems where we have a feasibility question. Therefore, it doesn't really matter what exactly you put in the optimization objective, but in this particular case, we have put down the total number of boxes that we are fitting into the truck. It doesn't, like, it could have been 0. If we minimize 0 over a feasible set, it gives us 0. if we minimize 0 or over an invisible set, that would give us plus infinity. So just by minimizing 0, we could see if the problem is feasible or not, which is the only question we are asked here. Let us switch to the constraints. First of all, we need to ensure that we essentially have an item J is being put into one of the boxes. So the sum over all of the boxes, the indication of the item J is in the box I must be equal to 1. I wouldn't be I won't be so sure that greater than or equal works, but let's say that it would. Let's ignore this because it really should be equal to 1. Second is the box capacity constraint. We need to ensure that we do not put more items into box. For each box I, we need to ensure that we do not put more items that it can that fits into a box. And also we shouldn't put any items if we are not taking the box with us. So on the right hand side, we would have bi if the zi is equal to 1, and the right hand side should be equal to 0 if zi is equal to 0. On the left hand side, there is the total volume of items that is being filled into a box. So it's a summation over all items J of the size, the volume of the item times the indication of whether we are putting it into the current box or not. Then the constraint on the truck capacity is telling us that the summation over all boxes, this is I, this must be I. I will correct this later. So this is summation over all of the boxes. Sorry, this is summation over all of the. Oh, J doesn't belong here at all. I wonder how I put down this slide at all. Okay, anyway, so J doesn't figure doesn't matter here at all. It must be a sum over all of the i's of zi times bi. Zi is the indication of whether we take the box I or not, and bi is its volume. Note that it's like here we are having not the total volume of the items that we have put into the box, but the volume of the box itself, because it's not reshapeable really. Right, and now we just need to make sure that we put down the constraints that zj and xij are binary, and we are done. Any questions regarding the plan for a move problem?
Just to clarify, for the third constraint, is it just, it should be sum from I equals 1 to m, or is it j?
You're right. So let me correct this. This is a sum over. So we have m boxes, if I remember correctly. Yes. So it must be j from 1 to m, and then there's no j here, and then this is the truck capacity constraint. So now it should be okay. Sounds good. Thank you for correction. Awesome. Any other questions? Okay. Let's switch to shift scheduling. In the planning of the monthly production for the next 6 months, a company must in each month operate either a normal shift or an extended shift if it produces at all. So like if it does produce something, it can operate into different modes. A normal shift costs 100,000 per month and can produce up to 5,000 units per month. An extended shift costs 180,000 per month and can produce up to 7,500 units per month. Note here that for either type of shift, the costs incurred is fixed by a union guarantee agreement, and so is independent of the amount. So it doesn't matter how much you actually produce. As soon as you pay, like as soon as you do produce and you have selected your mode, then you need to pay this much. It is estimated that changing from a normal shift in 1 month to an extended shift in the next month costs an extra $15,000. No extra cost is incurred in changing from an extended shift in 1 month to a normal shift in the next month. So we can basically view it as like over time we either go and continue on an extended shift, or we go to a normal shift and then continue on a normal shift. And shifts from normal to extended would incur as a loss of extra $15,000. Now we have a demand to satisfy. We would need to plan for our shifts for several months ahead, given that we have a certain amount of demand that we would need to satisfy. The cost of holding stock, we also have a warehouse where we can just hold our production. The cost of holding stock is estimated to be 2 per unit per month, based on this on the stock held at the end of each month. And the initial stock is 3,000. So 3,000 is something that we have in month 0, and then we can choose to use it in month 1, or we can choose to store it for a month, and then we would incur the cost of the loss of $2 per each item. And we are given that the previous shift in month 0 was the normal shift, not the extended one. The amount in stock at the end of the month 6 should be at least 2,000 units. So here we have month 7, and in the very beginning of the month 7, we need 2,000 of our inventory. The demand for the company's product in each of the months is estimated to be as shown below. So we need to plan to satisfy this. Production constraints are such that if the company produces anything in a particular month, it must produce at least 2,000 units. So if we are producing anything, we need to produce this much. If the company wants a production plan for the next 6 months that avoids stock out, formulate their problem as an integer programming problem. Is the problem clear in general? I know it's a long one. So the words, but we should be able to formulate it as an integer programming quite compactly. Okay, so let's define the variables. First of all, we're gonna have the amount that we produce at month t, which is gonna be an integer value, but like any integer value, it doesn't have to be binary, and we will not put xt. IT is going to be the inventory period at month t. Basically, this is the inventory that we are carrying over to the next month. Y1t is going to be the binary variable that is equal to 1 if the normal shift is used in period t, and 0 if not. So basically, this is a variable that is indicating if we are in the normal shift. This is the variable that is indicating that we are in an extended shift. ZT is the binary variable that is equal to 1 if we change from extended to a normal shift in period t, and 0 if not. So this is the variable that is telling us that about this jump and like on the timeline that I was talking about. Because we incur additional costs during this jump. So it is important that there is no unit cost of production not anywhere in the problem. Therefore, we can assume that the production is free, and we can produce up to 5,000 or 7,500 depending on the shift type, like any amount. There is no indication in the problem if there. Okay. So if we note that there's nothing in the problem that is telling us that like what happens if the shift is idle and we do not produce anything in a specific month. So we're gonna assume that there is no cost in going idle at all, although it's not very realistic. But okay, so let's formulate the objective first. The objective would be to maximize the reward. Our reward is, okay, this is weird. This is not a reward. This is definitely a loss. Okay, so we're gonna be, instead of maximizing the reward, we're gonna be minimizing the loss. The loss consists of a summation of the t period of times, where t is equal to 6, of the following expression. The amount of money of loss incurred if we are in the first time in the normal time in the normal shift, and the loss incurred by, like, if we are in an extended shift, plus the loss of changing the shift from the previous time frame, and plus the cost of storing the inventory. So this is our total loss. Now we need to settle on the constraints. First of all, we need to make sure that we are not situated in both shifts simultaneously, right? So the sum of y1t plus y2t must be less than or equal than 1 for all t's. Then we are saying that this we also need to put down the constraint on zt. This constraint is telling us that z1, like, we remember that our first, like, our zero shift, our 0 month was in a normal shift. Therefore, 0 to if we have decided to stay in the normal shift, then we are not like, our z1 cannot be our z1 cannot be anything. Like it has to be equal to 0, because z1 would indicate that there is a chunk. So we are saying is that what we are saying is that basically if we have, so our z1 is limiting the value that we are giving to y21. If z1 is equal to 0, then y21 must be equal to 0 too. If z1 is equal to 1, well, the z1 could be equal to 1 too, but it wouldn't make much sense, just because we would have incurred loss. So our minimization objective would be like greater, and at the same time we would remain in the normal shift. So we would incur loss but not gain anything from it. So that would be a feasible solution, but that would not be an optimal solution. And this is something that, like, this is the way of thoughts that is all pretty much often used while you're formulating problems like this. Reasoning about what can be an optimal solution and what cannot be an optimal solution often helps you in formulations a lot. Okay, so I hope I did convince you that this constraint here enforces z1 to be equal to 0 in case we are in a normal shift, and z1 being equal to 1 in case we have switched in the to the extended shift in the month 1. Now let's take a look at this constraint here. it is telling us that similarly, if the difference between the type of shift in the previous month and the type of shift in the current month is equal to 1, meaning that this, like, the sum of y1 t minus 1 plus y2 t is equal to 1, then the value 1 plus ct is allowed to be equal to 1. In other words, zt is to be equal to is allowed to be equal to 0. Okay, I need to clarify on this. So basically, what is being said here is that well, our zt must be equal to 1 if and only if y1 t minus 1 is equal to 1 and y2 t is equal to 1. So we have switched from a normal shift in the previous time step to the extended shift in the current time step. So we can only allow like if we did not make this shift, it will make much sense to make zt being equal to 1, because it would worsen our position. So we only need to enforce this statement only in one way. So if we have this condition hold, then zt must be equal to 1. And how do we say it? Well, we are saying that, so in case this thing is happening, then this summation here is equal to 2, and therefore 2 must be less than or equal than something which is upper bounded by 2 actually. So therefore we are saying that in this case this summation also must be equal to 2, and therefore zt must be equal to 1. This way, this couple of inequalities are enforcing z to be the way we defined it. So this is basically the definition of z being expanded into this long story. Everything else is supposed to be much easier. First of all, so this is the logical conditions that we have spent so much time on. This is basically the reason we have spent so much time on this logical conditions, because they are the hardest. The next constraint is enforcing that we are not producing more than we are allowed to. Our xt must be less than or equal than either 5,000 if our y1t is equal to 1, or 7,500 if we are in extended shift and our y2t is equal to 1. Then if we are producing anything, then we have to produce at least. Therefore, if we are in either of the non-idle shifts, our total production must be greater than or equal than 2,000 for all of the time steps. And now we have this equation, this balance equation on the first time step. We have 3,000 that we carry over from the previous month, and we have the inventory that we are carrying over to the next month. We have the inventory that we have distributed according to the demand, and we have the inventory that we have produced. Then similarly, we are writing down the balance equations for all of the next months, and we are saying that the inventory that we are carrying over to the 7 months must be greater than or equal than 2,000. Then we are saying that our inventory and then amount of production must be greater than or equal than 0, and we are reminding ourselves that our variables z, t, y1, t, y2, t are binary. And also what I'm missing here is saying that xt is actually a number, an integer number. This would conclude the formulation for this problem. Are there any questions here? I would like to comment that this line of thought that we have exercised here when we are reasoning about logical condition. When I was saying that something cannot be an optimal solution, this kind of line of reasoning cannot be underestimated because it's very powerful, and it is often being used when you're constructing formulations, because formulations are kind of restricted in a way because they normally use inequalities, and inequalities are normally only one way, and the conditions like if and only if are very hard to formulate if you are not using this line of thought. So whenever you have if and only if, it is very useful to think about what is necessary to, like, which way, this way or this way, the implication is actually necessary to enforce, and which way it would hold automatically. Okay, so then I have two problems of your choice. First is the uncapacitated facility location, and the second one is the problem 197 from the textbook. I would say that this uncapacitated facility location is actually commented on in the book. So you can just read about it, and I will try to spend just the past 7 minutes on this one. So we have a QAD company that draw up a production program for the next 9 weeks. Jobs last several weeks, and once started must be carried out without interruption. During each week, a certain number of skilled workers are required to work full-time on the job. Thus, if job I lasts PI weeks, LIU workers are required in week U for U from 1 to PI. The total number of workers are available in week T is LT. Typical job data is basically all of these numbers that are put down in the table below. We have to do all of these jobs. We just don't know when, in which order. So we need to plan ahead exactly how we're gonna distribute our people among jobs. First of all, we need to formulate the problem of finding feasible schedule as an AP problem. Let's introduce the variable which is binary, which is telling us that so xit is going to be equal to 1 if job I starts in period T. Each job must start in some period and terminate before the end of the time horizon. Time horizon is 9 weeks, I believe, right? Right, probably. So yeah. So the summation over all of the time periods that are feasible for a job to start so that it finishes before the time horizon, which is indicated here. The summation of over all of the XIUs must be equal to 1. Basically, we are saying that for all of the jobs, we are saying that each job must be started somewhere so that it can be finished. If job I starts in period U, the number of workers required by job I in period T is LITU T minus U plus 1 for T in this interval. So the bound on the number of available workers in period T gives us this inequality, which is saying that the sum over all of the jobs the sum over all of the periods of times when these jobs are being performed, the number of workers times the indication, the number of workers that the job is required for, times the indication that the job has started in the time period U, must be less than or equal than the total number of workers that is available to us in the time period T. So basically, this is all of the time periods that have when a job could have been started. So if we put ourselves in a time period T, this summation here expresses all of the jobs that could have had started, so that they are still being executed in the period T. This is what this expression expresses. The remaining constraints are enforcing that xit is a binary variable, and xiu is equal to 0 if u is greater than, like, we cannot start anything after the job is cannot be completed before the end of the time frame. Are there any questions regarding the formulation, how we did this? Cool. Okay. So now the problem, the part 2 of the problem was to formulate when the objective is to minimize the maximum number of workers used during any of the 9 weeks. So we would like to make the number as small as possible. So we just express the number in the period T. Here is this number. So we just copy from here. This is the number of workers used in period T, noted with eta T, and we add the constraint that eta T is less than or equal than eta, and the objective function is minimize eta. In other words, we are facing a maximum problem that we have seen during the lecture. So it is minimize the maximum over 9 eta 1, so forth eta T. And now we can reconstruct it into minimize eta or z such that z is less than or equal than eta T for all T's. Okay, cool. And the last part of the problem is that job 1 must start at least 2 weeks before job 3. This can be formulated as follows: if job 1 has not started in the first T periods, job 3 cannot start in the first T plus 2 periods. This is how we can formulate this expression. This is yeah. So this is the summation. This is the expression that is telling us that job 1 has started during the periods from 1 to T, and this is the expression that is telling us that job 3 has not started essentially after the specific time frame. I think this is it. Okay, there's also the fourth and the fifth parts, but you will have to take a look at them yourself. Let me know if there are any questions. I will stay here for the office hours. I'll see you next week for the hopefully in class lecture and discussion sections. Thanks a lot for your attention.
Sorry, thank you. I have a real quick question. Our last constraint, regarding the starting the job 1.
In the part 3.
Yeah. Sorry. This the most recent one.
Right.
Why does there need to be a summation? Or I think maybe I'm not like fully grasping it, but in my mind I would just assume it's like the binary variable that says you started in like T equals 1 should be, or I don't know. I might be not understanding the.
So look, we are sitting in a period time T. we imagine ourselves in the period time t. What our constraint is telling us that job 1 must start at least 2 weeks before job 3. So if the job 1 has started by now, then job 3 cannot be started. Okay, let me put it this way: if the job 1 has not started yet, then the job 3 cannot be started yet, and it will not be able to be to start itself until the time period t+2. This is what this expression is telling. This is indication of the fact that job 1 has been started before time t, and this is the indication that job 3 has been started before t+2, right? Because this thing is equal to 1 whenever there's some u for which xu1 is equal to 1 in the past.
Okay, I think I kind of get it. I think I kind of get your reasoning. It's like, or I get the reasoning of like you have to prove kind of like if and only if. So it's like it's both that like it starts at least 2 weeks before, or it's like I guess it's like they're taking the contrapositive almost, right? Or not really. I'll probably have to think about it more because I think I get the general idea, but it feels like it's over asking. But I think I'm also just not thinking about it too clearly.
Let's think about it for an hour, and then if you still have questions, just write me an email and we'll discuss it further. Sounds good?
Yeah, no, thank you. Yeah, thank you so much.
No problem. See you next week.